right, cool. Welcome back. A little blustery out there. Some snow yesterday and today. Getting chilly. So on Monday, today's Wednesday, 2 days later, Wednesday, we started talking about this Francis Scott Key Bridge, kind of a big disaster. Like, boat just lost control. It wasn't traveling fast, but engineers were sort of blamed of like, why wasn't there infrastructure to stop this boat from crashing into this bridge? So first, back of the envelope calculation that we did was like, all right, if we had a tugboat always near the bridge and we wanted it to, within 1 minute, bring this thing to a stop, we could say, all right, momentum is coming at the bridge, our tugboat is pushing against it. It's not going to push exactly against it, so it would have to keep like kind of going back and forth, but overall average force is this. So we would need roughly 6.5 million newtons. How does that sound is that an achievable amount of thrust with a boat? Maybe? What do we think? Did anybody look up, like, tugboat? What is thrust of a tugboat? Doing it now?
Was it 30 million?
Is it 30 million? For what is it?
For a rocket.
For a rocket? Okay. So if we had a rocket, we could just send the rocket out and we would only need a fifth of its capacity.
So the tugboat usually does 50 to 60 kilonewtons.
Kilonewton.
77 metric tons.
Metric tons? Yeah, so kilonewton. So it's about 1,000 times too small. So we would need 1,000 tugboats? Is that right? Lots of is it in Wikipedia? Does it have like a total thrust? Cyclometer? I don't know. I need like total thrust, right? How do tugboats generate so much thrust? How much thrust do they create? Where'd you find the, here? An AI overview? $65 tons. So I think roughly that's like bollard pull. Anyway, okay. I'm not finding but roughly it seems like we need a lot of tugboats or more time. Like if it was 10 minutes, maybe we could do that. Okay. Then the other option that we have is, well, why not just create like a big bumper pad? Like, why can't you just put like rubber tires around the pier, around like the supporting structure, and then bring it to a stop, or get it to like bounce off of instead of destroying? So if we have like rubber fenders that have some stiffness to them, like 3 times 10 to the 6th, and I did that based on like just like a stack of rubber tires, kind of all placed in parallel. And they all. So how big is delta x if that's our k? Let's grab our values again, right? $96.5. So imagining that we could mount this thing on something that's not going to totally destroy the bridge, like we have some kind of comically large spring that we can bounce it into. What's going to happen? How do we get this to stop? So what do you think? How do we go through this one? Yeah. Okay, is that one always true? Like delta x squared? Are there any other terms in here? Like what's our full equation for work and energy? Like how did you plug in, where did you plug in what here?
Just kinetic energy versus the spring energy.
Yeah. So yeah, exactly. I mean, it seems so. The way I always check it is like I have a T1, then I'll have some kind of V1. There's some work being done to go from 1 to 2, and then that turns it into T2 plus V2. So this is all the things that can happen. In the beginning, if we're saying the spring is not stretched at all, and that's kind of what we said in this equation, then we could say that there's zero potential energy. It's like a boat with speed that's coming at us. Then at the end, we're trying to say that there's no kinetic energy. So we can say T2 is 0 because we're trying to bring it to a stop. And then the work, that non-conservative work, at least during the spring, what we're trying to solve for, we can say that that's probably about 0 or close to 0. Or at least conservatively, we can say this whole thing is 0. And that's how we get this kind of working backwards from the initial equation back to what we first said. How's that? Not like blowing any minds here. It's hopefully what we expect. But I always like to write out the full equation and then set terms equal to 0, just so that I know what assumptions I'm making. So T1 equals V2. Yeah. Okay, what do we get for delta x? How many rubber tires do we need? 3 or 4, 5 or 6, a billion.
That's it. It says 4 to 6 units 6.
Yeah, 4 to 6 times 6. All right, number I've heard so far is like 20 meters, 20.3, but 20 meters. How does that sound for like bumpers around this pier, around this bridge? It's good? Install it?
Doesn't seem too crazy. I mean, that's like
60 feet, yeah.
But it has the amount of pressure from the flowing water. I don't care how big it is, it's going to break it over time.
It's gonna break, yeah. I mean, I mean, 60 feet of rubber. It's a lot of rubber. Like not quite a basketball court, but not too far. I mean, half court of rubber, just like. Oh yeah, here was the disaster that did happen when it did crash. But if we have a 60-foot rubber island around it, how much room is left for boats to go through? Because you need 60 feet on every thing. So if you had 100 feet to pass under, now you have, I mean, yeah, so it's 60-foot radius, right? So now on either side, 60 and 60, they're overlapping. We basically need like to support the entire thing with rubber. So it's not that it's impossible. It's not that you can't design this kind of stuff. It's that maybe, I mean, this is probably like a few hundred feet. But if we had 60 feet kind of stretching out, like this thing here is probably like a 6 or 5, maybe like 6 or 8 foot wide support. So it'll be 6 to 10 times, probably about 10 times larger than this. And then on either side, we would need like big floating supports there. So it's a lot to try to stop this thing. So it's not so easy as just like there should have been something in place. It's like, well, yeah, if we knew the crash was going to happen, we could have put 60 feet of rubber there, or yeah, but we didn't. Like the whole point was it's supposed to be able to stop itself. This is pretty real world, and like you have the tools. Maybe even before this class, you kind of had the tools to solve this kind of problem. But this is like the dynamics kind of problem solving that you'll be asked to do. Of like, hey, stop this boat. Like, well, how do you want me to stop it? I could send a tugboat out. I could add some rubber, but we're going to need a lot of tugboats. We're going to need a lot of rubber. Around 20 meters. I'll put a little. And really, that didn't account for any factor of safety. So double it. Now we're talking 120 meters, 120 feet. And how are we doing? Should be able to just finish this out, right? Finish this today, and we'll be done with it. Done with homework. All right, so we have a bar that is sliding down this wall. Usually this is like the frictionless ladder problem. The main thing to remember is don't use a ladder if there's no friction. Maybe that's why you come to engineering school, so you can learn these important lessons about like why you shouldn't use a ladder on an icy day. So there's no friction here, there's no friction here, and it starts sliding down. We want to figure out like how fast is this thing moving after this angle starts at 0. So like theta 1 is 0, theta 2 is pi over 6, or 30 degrees. So it's at 0, something happens and it starts to move. How fast is it moving when it gets to like an opening of 30 degrees? How fast is it like spinning? What do we think? How do we even start this? What do you want to do? Bless you. If we're not sure, go back to basics. Main thing we always start with is kinematics and free body diagram. So like how is this thing moving? How many degrees of freedom does it have? And what forces are acting on it? And from there we can jump into like Do we want to use impulse momentum, work energy? Do we want to create an equation of motion and integrate it? Like we have all those different options from there. So first step, at least I call it step 0. How many degrees of freedom do we have? One. I like 1. Makes sense. Think. Yeah. So if I increase angle, I have to move down the wall. And if I try to move the thing to the right, I have to decrease the angle because I'm always in contact with the wall and the floor. All right, so we've got 1 degree of freedom. We're talking about like angle of this thing moving, so it kind of makes sense to call like our degree of like the thing that we're trying to solve for like theta. Like if I know the angle, I know everything I need to know about it. So I can kind of say like, all right, we'll call it theta. So it's a rigid body, so we can't say that it's a point mass anymore. What are the forces acting on it? And where are they acting? Because now a rigid body, we need to consider both kind of the torque and total force. So try drawing like what forces we have there. This one would be like friction. Yeah. Yeah. Maybe we can add friction. Yeah, that would be friction. All right, so I saw something like some kind of floor has a reaction force, wall has a reaction force, and then gravity acting down. And I said there's no friction, but doesn't technically say no friction. You could add it if you want to make things more difficult. But well, at least we're not like bouncing. We don't have to reverse the sign of friction or anything. Which forces are doing work on the bar? Like, which ones are changing the kinetic energy of this bar? Are all three of them? They're all being applied, right? They're all creating acceleration, because F equals ma, so every force contributes to acceleration. But what about its kinetic energy? Like, which ones are doing work to change kinetic energy?
I'd say R1 and MG.
Only R1 and mg? So R1, so we'll say like work to get from 1 to 2 is R1 times some distance plus mg times h, which is like the distance that it traveled. Which direction is R1? R1 points kind of to the right. Which direction is that top of the bar moving? Straight down. Yeah, so the distance, and you're right to think about it, like, it could do work, like it is a force, it can do work, but the distance that it travels is always perpendicular to its applied force. And same thing with R2, like that contact point is only moving left or right, but R2 always points up. This is always true for any contact force. Like anytime you have a normal force or things kind of, or a hinge or sliding contact, the thing that's the force that creates that sliding, like the sliding contact, it's not doing work on the system. It's definitely changing the acceleration, like it is a force, so it does like MA stuff, but it's not changing kinetic energy. It's not actually like doing work on the system. And really this, yeah, call it MGH. Or I could call that like a V1 to 2. So if it's gravity, we can call it like there's a change in potential energy. Or you can say that it was work done by gravity, either way. They're both 2 1. If an elevator is speeding upwards, then the force would be doing work. I think so if we're like creating torque to speed someone upwards, there's a constraint force between the person and so there's a question in the chat about like if you're in an elevator and the elevator starts accelerating up, didn't it do work on you to increase your kinetic energy? But that one, like if we're only looking at the person, like just in here, then we could say that there's like some N from the floor equals MA because it's moving up. But as a total system, if we're thinking of it of like, this is my system. There's work in here and no other like external work that way. And the person has to maintain. The contact force is just making sure that the person and the elevator move together. So it's not actually doing work. Whatever work was done to the person, there's that negative work done on the elevator itself. Anyway, just the side quest over here. All right. And I kind of led us down like a work energy form, but just to think about like the motion of this thing as the angle's increasing, where does this thing go? Like as it slides down this wall. When it's vertical before it starts moving, what is the height? Like what do we say MGH1 is? Like how much potential energy do we have?
Yes, it'd be the length of the stick.
Total length? So this. Yeah.
Would be the height of the center of gravity, where it's at that shot.
Height of the center of the stick? What do we think about that? Does that work? Why would it be the center and not the top?
Well, the center would be in the middle, and the middle, it's clear that where the middle is from ground and only half the stick.
Yep. Yeah. Okay. So it's half. So the middle is going to be half. But why the middle? Like, why would we?
It's where the gravity is acting.
That's where gravity. So it doesn't act on the ends of the stick.
Okay.
So here's a weird question. So if I have two objects, they're both 1 meter off the ground, but one's at an angle, the other one's straight up and down. Which one has more potential energy? And this one could just be gut instinct. Let's go A and B. Who says A has more potential energy? Center of mass is the same. It's the same height for both of them. So who says A? Maybe 3 or 4. Who says B has more potential energy? Did anyone want to say something different? They're equal. Same potential energy. Like the angle, and even if it's flat, like the amount of energy that it took to get the thing up there, it doesn't matter what orientation it's in. It's the center of mass that matters, because you have as much work to get the top at a different angle as it took to lose energy from bottom to a different angle. So at least for like rigid bodies, they act exactly the same as a point mass, It only matters where its center of mass is. That's all the potential energy is. So mgh and that one I'm just sort of like, take my word for it, but you could derive it if you wanted to like integrate how much potential energy each of the little pieces of it, and you'll find that all the stuff that you lost going from like at an angle to vertical is all the stuff you gained by putting one side over on the other, because there's a lot of symmetry involved there. Okay, so L over 2, long answer. But now, what is H2? When it gets to 30 degrees, how high off the ground are we? Because we still only care about that center of mass, right?
Well, they just looking at the geometric, we're asking the height is going to change quicker in the big range. Like once it gets still lower or higher, like once it's not 30 degrees, once it's shorter, it will change a lot slower. Okay. So it changes quickly.
Yep.
Yes, that's
Linear.
yeah, it's not linear.
Proportional to data.
Yeah.
I got it because
So like L over 2 cosine 30 was kind of what I was seeing floating around. Yeah.
why would you not have a cosine 30 over L?
Divide by L over 2.
Because we're solving the hypotenuse when we go back and above,
So if I turn this into, oh, if we think of it as like one big triangle that is L, and L cosine is like total, like where it's, how high its contact point is. I could look at two similar triangles, similar as in like they're smaller but same proportions on the inside. So top one is still L over 2 cosine, and then L over 2 cosine. Does that make?
I kept each one of the variables. I didn't change.
Oh, okay, yeah. Yeah, like this distance is 2h2, so it's not h1 anymore. Yep. So actually we have, like if we think about this, like what is the position of our block? We know that it's going to be L over 2 times, and this one's like my x-axis, my y-axis. So along the y-axis, it'll be cosine theta j. And along that x-axis, it would be that sine theta component. So now we kind of know like how does the position change as theta changes? Do you know what sine and cosine look like? If we change theta from 0 to 90, what is this thing? What does our center of mass do? As angle goes from 0 down to 90 as it goes down the wall. I'm kind of crudely drawing it, but it makes a little circle. So it starts at a radius of L over 2 and slides along circular path until it hits the floor at radius L over 2. What? And there are some cool like mechanisms like sliding pistons with one bar, so of horizontal and a sliding rack, and as those pistons move left and right and up and down, the bar travels in a circle. And that's always cool. And then so this is kind of the path that I was leading us down, is what is the position, how fast is it moving? So our initial kinetic energy, that one's 0. Initial potential is mgh1, which we just figured out. We're not adding any work to it, like there's no motor, we're not pulling on it, there's no friction. If you want to add friction, you're welcome to. And then at the end, we'll have some kind of kinetic energy, and we'll have some potential energy, unless we want to say that whatever amount we dropped is getting to 0 or something. But what's the other part of our kinetic energy here? We've got 1/2 mv squared. That one's always there. What else do we have? That rotating, yeah. 1/2, and in this case it's ml squared over 12 times that, like, theta dot squared. So now I need some way, because I can plug this into my equation, but I have two unknowns, velocity and theta dot. So now I need some connection between how fast I'm going and how fast I'm rotating. V is derivative of R. I figured out R. I kind of extrapolated from the two data points I had. So it should be an L over 2 theta dot, and then what's this? A negative cosine theta, and a positive sign, or no, positive and then negative. What's v squared? How fast is this thing going? For a given theta dot. Does it depend on theta, the speed? What's cosine squared plus sine squared? 1. Okay.
V squared.
So v squared is L squared over 4 times theta dot squared. At like speed, how fast we're going is that L over 2 theta dot. Now at least we have everything in terms of angle. Like we have theta dot, we've got one equation where we can plug everything in. Like mgl over 2 is 1/2 m theta dot squared, L squared over 4. We could pull out the L squared, right? 1/4 plus 1/12, and then plus mgl over 2 times cosine 30 degrees. And then we just have one equation, one unknown, because we did all the work to get it into this form. Like we did a lot of pre-work to get to this, but one equation, one unknown. Now it's algebra. So we can ask a calculator or just our friend who's really into math to do it for us. We did all the physics, all the engineering work, we got through it. And it's kind of speed running at the end because we're at time now. Right? Yeah, still 110. Cool. Thinking about it, or what questions are there as we're kind of wrapping up the last homework problems? Sorry, what was it?
It's like mass to the capital crossroads, right?
Yeah, it should be independent mass, right?
Yeah, but so do all the L halves.
L over 2's. Yeah, we can get rid of one set of L over 2. Then we end up with an L. Like that. Yeah, that works. Yeah, it should be size of it, right? Is everybody radiant or they're going to go up? Degrees? No, it should be radian. Usually radian.
It should be radians.
Yeah, at least like unit wise, it's radians.
Not really about. No, the answer should be radians.
Well, so even if we use degree mode to calculate this cosine, it's a unitless. That should be a unitless number. And radians are the only like unitless measurement of angle.
You look at oxymoron.
What?
You look at oxymoron.
Oxymoron? Radians are? Or the, yeah. Yep. Okay, cool. We'll be back for more dynamics on Friday. Thanks a lot.